Hello everyone, my name is Razaul Mustafa and I will present supervised machine learning approach for dash video QE prediction in 5G networks. In the agenda I have introduction, background, what is my purpose, methodology, phases, classify results, ABS analysis and conclusion. Online video streaming has become the most dominant application on today's internet. Video streaming becoming very popular and sites such as YouTube and Netflix share nice share of internet traffic. 5G is expected to support high throughput and low delay, contributing to enhanced QE expectations. One of the key challenges in 5G is adapting to the increased growth of video streaming traffic and maintaining smooth quality of experience. Streaming services adopt the dash paradigm to deliver online video content. Adaptive bit streaming algorithms aim to detect a favorable quality of video streaming. They use network status QoS, delay, throughput, and loss, and provide user a nice video quality without any stalls. In the 5G future network, QE management is crucial to the optimize better video quality. So it is necessary to understand the ABS algorithm behavior, the impact correlation between QoE and QoS KPI. QoS KPI we have delay, throughput and loss that affect QoE KPI which are bitrate, resolution, stalls and that both influence user and QoE which is subjective mouse. What is logic behind Dash? Dash works by split video file into many small segments, 2 to 10 segments each. Each segment encoded with different bit rates and resolutions. The representation of each segment described in an MPD file and they are stored on the server side. ABS algorithms are responsible for dynamically selecting the appropriate segment based on current network condition. If network condition very nice, then the ABS algorithm select segment with high quality and high bit rate. ABS algorithm of three strategies: rate based, buffer based, and hybrid. What is the purpose and contribution of this work? We examine the in-depth analysis of 6 state-of-art ABS algorithms streaming with varying bandwidth in static and mobility 5G scenarios. The analysis is undertaken through the assessment of associated QE models such as a P.1203 QE standard, and finally a proposal for machine learning classifier to estimate QE based on QoS RTT, number of packets, and throughput. The methodology phases are three phases. Phase 1, we have parallel client stream dash video. Phase 1, stage 2, collect go dash log files per segment QoS feature collection, and we save these QoE and QoS feature in the MySQL. And phase 3, we input the model RTT, throughput, and number of packets, and the model predict P.1203 QoE. In phase 1, we have mininet Wi-Fi to emulate the streaming network scenario. We have two OpenV switch 1 and switch 2, and Go Dash client, parallel Go Dash client streaming from the same server. We have server caddy and link band with switch 1 and switch 2. We applied 5G cellular network traces at this point, switch 1 and switch 2. We made 10 cases to stream the net to generate the data stats. We have driving cases in Mbps 0.5 to 3 Mbps, 6 to 14 Mbps, 38 to 10 Mbps, and 29 to 10 Mbps. Similarly, in static mode, we have 0.5 to 6, 8 to 57, 4 to 7.6, 52, 0.5, 7 to 20, and 72 to 9 Mbps. We use Linux TC to change the link at this, to change the bandwidth on this link by after every 4 seconds. We have a caddy server here which have animated video name Scientel encoded using H.264, and segment duration we use was of 2 seconds, which the Scientel video has 8 resolution across 30 representation rates. The Go Dash player provides a lot of state-of-art ABS algorithm, but we use 6 state-of-art ABS algorithm: conventional and exponential, rate-based, BBN logistic, buffer-based, arbiter, and elastic hybrid. During each experiment, the Go dash player produces a log file which has the following features. We have per segment objective QE KPI, which is segment arrival, time, style, stall, bitrate, resolution, etc. And we have per segment output from 5 QE models, quality fixation model, which have P.123, Jin, Ju, Dem, and Clay. We use tcdump to collect pcap at these points switch 1 and generate pcap files known as network level QoS KPIs. We use a Python scapy package to fetch per segment QoS to QoE KPIs. And then we finally stored QoE and QoS both in the MySQL database. This is the example of our database which have the information of Go-logs and pcaps. Here host 1, it's showing the host 1, the host 1 experiencing 0 star bitrate of this, and segment we showed just 5 segment. Total user in this experiment was 2. Buffer level algorithm was BBA, and these are the QoS feature, RTT throughput and packets. These are per segment features, RTT throughput and packets, and later we use 3 features to predict P.value3 model. We can see that these values are in the continuous for 1.878, 1.890. So that's why we use regression models to predict P.value3 model. We use three well-known regression classifiers: multilinear regression, decision tree regression, random forest regression. And the accuracy of our model, we use mean absolute error. First, we have the results by ABS type. We have hybrid, arbiter, and elastic. We input the model arbiter and elastic QoS feature and predict the P.value3 QoE model, which in the case of static and mobility. In the case of static, we have 0.17 mean absolute error. In case of mobility, we have 0.31. In each case, we can see that random forest regression have a better mean absolute error as compared to DTR and MLR. Similarly, buffer based, we have BB and logistic and conventional expansion. We can see that random forest regression outperform other algorithm in this case. The next we have the case of static and mobility. In case of static, here again random forest regression has nice accuracy. In the case of mobility, random forest regression has 79.08% accuracy, which outperform DTR and MLR. Finally, we have ABS analysis. We have dirty bit stream analysis in case of hybrid, elastic, and arbiter plus buffered, BB and logistic throughput based are conventional expansion. The results I will show in next slide. The settings are, we have two concurrent clients. One client experience is shown here. We stream 67 for 2-minute video, and the Scientel video is used, which has 13 different representation rate across 8 resolutions. And we show RTT stalls and P.203 mouse score. And we use the driving mobility case 0.5 to 3 Mbps and 6 to 14 Mbps. What is the RTT behavior in ABS? We can see that 6 to 14 Mbps, the RTT per segment of 0 to 60 segments, we have the exponential and convention perform similar. Similarly, lasting arbiter performs similar sort of RTT. But in case of BB and logistic have more RTT as compared to BBA. Similarly, in the less bandwidth scenario 0.5 to 3 Mbps, same sort of RTT, but in case of logistic, little bit higher RTT in the first 0 to 15 segments. What is stall behavior in ABS? We can see that exponential and conventional same sort of stall, but arbiter plus have little bit higher stall from 40 to 60 segments, and but we experience no stall in case of BB and logistic. And similarly, in case of 0.53 Mbps, same sort of stall in exponential and conventional, but in case of arbiter plus, it has stall from 30 to 50 segments, and but BB and logistic have same sort of stalls, but few stall higher than logistic in case of BPA from 20-30 segments. What is P.203 behavior in ABS? We can see that stalls in this case arbiter plus, causing these segments to switch to lower QoE value. We can see from here. that 40 to 60 segments we can experience stalls and discuss the segments to remain into lower p.value 3 values. But all other algorithms behave similar. What is conclusion of our work? We use ML to train an algorithm agnostic classifier that predicts user key or video session based on network QoS metrics, which are RTT number of packets and measure throughput. For future, we would like to analyze the impact of other objective KPI on QoE. Thank you. Any question? You can send an email at this my address.